At this point in the quarter, we're going to start building up some skills to do essentially a two-dimensional equivalent of a line integral, which is called a surface integral. So instead of adding up the values of a function over a line, we're going to add up the values of a function over a surface. And surface integrals will come with their own set of theorems, akin to Green's theorem, which have the potential to make the surface integral a lot easier, in the same way that Green's integral had the potential to make certain line integrals a lot easier. And in order to prepare ourselves to talk about those useful theorems, we're going to need to introduce a couple of terms and formulas, and today we're going to introduce two such formulas called the curl of a vector field and called the divergence of a vector field. So by the end of the day, we're going to want to be able to define the curl of a 3D vector field, which is defined in terms of the cross product. And we want to be able to calculate the curl, and then we're going to use curl together with continuity to determine whether a three-dimensional vector field is conservative. So in this section, we're going to start to deal with three-dimensional vector fields. And let me just take a moment to be clear about what a 3D vector field is. We had our 2D vector fields, and they took in a point with two components, and they produce a vector with two components. 3D vector field, instead of going from R2 into R2, a 3D vector field goes from R3 into R3. It will take a point x, y, z in three-dimensional space, and it will run it through a rule, and it will output a three-dimensional vector with some function of x, y, z in the x component, with some function in the y component, and with some function in the z component. And these are traditionally called P, Q, and R. So it assigns to every point in three-dimensional space a three-dimensional vector. Now suppose that we have a three-dimensional vector field f, function of x, y, z, producing component functions which we're calling p, q, and r. Let's define another vector, and we're going to define it using physics notation where we have I, j, and k. Now, I've written them here using boldface, but in case you can't see it, I will emphasize that I, j, k here are the standard basis vectors for R3. Now, this nabla is defined by putting the partial derivative with respect to x in the x component. So we're putting an operator here, an instruction in the first component, putting the partial derivative with y in the y component, and the partial derivative with respect to x, with respect to z rather, in the z component. Then the curl of f is the vector defined by the formula curl f, that's how it's denoted, is equal to nabla cross product f. This is the cross product. Now recall that the cross product for two vectors could be thought of as the determinant of a 3x3 matrix, where you had the vectors I, j, k in the top row, and then you had the components of nabla in the second row, so partial x, partial y, partial z, and then you had the components of f in the third row, so p, q, and r. Now, this is the way that you really want to remember curl. But perhaps it's been a while since you calculated the cross product, and you've probably never calculated the cross product where there were operators like partial y involved. So let's just take a moment out to really expand upon what this notation is telling us to do. Okay, now when you took the cross product, we started with the x component corresponding to this vector I. And the vector I lives in the first row and the first column. So you focused your attention on the portion of the 3 by 3 matrix which excluded the first row and the first column. And then you went in and did a sort of diagonal products, and you do partial y of r, partial y, and then you subtracted the other diagonal product minus partial q, partial z. Okay, let's try and just clean that up and remove those annotations that I made to help you see what I was looking at. Alright, now for the j component, what we do is we take the partial x in column 1 with r in column 2. We subtract partial z in column 3 with p in column 1. But because it is the j component, we have to make the entire quantity negative. The second one is the opposite, so it goes plus minus plus and alternates. And finally for k in the third row and column, we focus on rows and columns 1 and 2. So we do partial x x of q, partial x, and then we subtract partial p, partial y, so minus partial p, partial y. Okay, now this is the long form of the curl. I have never memorized this in my entire life. I don't think it's worth it. I think the easiest way to remember the curl is to remember it as the cross of this nabla with the vector field that you're working with. Alright, so as an exercise, let's calculate the curl of the vector field given by xy, xz, xy squared, and 2x here. So let's go ahead and calculate what we would get if we had I, j, k, if we had partial x, partial y, partial z, and then we had x times z, xy squared, 2x, and we took the determinant of that matrix. Alright, so looking at the I component, we have the partial with respect to y of 2x. The partial with respect to y of 2x is 0, since 2x contains no y's. And going in the opposite direction, the partial with respect to z of x squared is 0, because xy squared contains no z's. Alright, let's look at the j component. The j component, so we have partial x of 2x, result 2. And then going across from that, partial z of xz is x. And then, because it's the j component, we swap that. And finally for k, we have partial x of xy squared, which is y squared, and subtract partial y of xz, which is 0. So after a little bit of tidying, we obtain the vector 0, x minus 2, y squared. That vector is the curl of f. Now, one thing to note is that curl f is a vector. Curl f is designed to take in vector fields and produce vector fields, more vectors which are functions of x and y. So curl f takes in vector fields and produces vector fields. So this is another situation where curl of f represents a vector quantity even though it is not labeled especially using boldface or using the vector overline or the vector arrow. You are expected to remember and have memorized that the curl of a vector field produces a vector field as well, and not a scalar. Okay. Now remember, for 2D vector fields, we had a condition that we could use to check if our vector field was conservative, if it was the gradient of some other function. If the vector field was conservative, then the mixed partials were equal to each other. And if the vector field was nice, then you could also go backwards and you can say, oh, okay, if the mixed partials are equal, then I can conclude that the vector field is conservative as well. And there is a similar equivalent in 3 dimensions, and a way to use the component functions p, q, and r to determine whether or not your vector field is conservative, if it has a potential function out there somewhere. And so this theorem is about that criterion. Goodness me. Okay, so we have our vector field f of x, y, z, and there is some fine print here. First, its domain has to be all of R3. Second, the component functions have to have continuous partial derivatives. If that vector field satisfies that fine print, then the following statements are logically equivalent. And remember, that means that if one of these is true, then both of them are true at the same time. And if one of them is false, then automatically they are both false. So the first statement is that f is conservative, which means that f is the 3-dimensional gradient vector of some other multivariable function called the potential function, once again. And the second criterion is that curl f is 0. Curl f is 0. And this time I will emphasize that this means curl f is the 0 vector. Curl produces vectors, so curl f would equal the 0 vector in this theorem. And I'll add the arrow to emphasize that. So what does this mean? This means that if curl f is equal to 0, there's a potential function out there somewhere, guaranteed. If curl f is non-zero, then there is no potential function, and it is pointless for you to try and look for one. So let's do a quick example with the following vector field. Show that the vector field f of x, y, z equals y squared z cubed, 2xy z cubed, 3xy squared z squared is conservative, and then find a potential function. So let's get started. So we have the matrix with I, j, k in the first column. We have our partials in the second column. And we have our component functions in the final row. So we have y squared z cubed, we have 2xyz cubed, and we have 3xy squared z squared. Now looking at the x component, the partial derivative with respect to y of this third function here would be 6xyz squared. And if I subtract the partial derivative with respect to x of the y component, I'm subtracting 6xyz squared. Good. So far so good. If the curl is to be 0, then all 3 components of the curl must be 0. Alright, now looking at j, we have the partial derivative with respect to x of 3xy squared z squared. So 3y squared z squared. And then we're subtracting the partial derivative with respect to z, so minus 3y squared z squared. And even when you take the opposite of that, the result will still be 0. So that's wonderful. And finally for k, we have partial x of 2xyz cubed, so 2yz cubed, and then partial y of y squared z cubed, so again 2yz cubed. So having calculated the curl, we found that it was the 0 vector, and therefore we can conclude that f, jumped again. I'm not sure why that happens. I still haven't managed to fix that. F is conservative, which means that our quest to find the potential function for f is not a doomed quest. A potential function is out there. Now the technique that we're going to use to find the potential function is exactly the same as the technique that we used to find the potential function when we had 2 variables instead of 3. We are going to try and use a technique of partial integration. Okay, so if I take the x-coordinate of the vector field that I am given, which is y squared z cubed, that must be equal to the partial derivative with respect to x of the vector field. So if I undo that with a partial integral, then I will get xy squared z cubed, but I will also get some constant term. And now I have to be extra careful because the constant can contain both y's and z's. Because a partial derivative with respect to x would treat both y and z as constants, the partial integral has to account for the fact that y and z could potentially be contained in this added constant term. Now, if I look at the partial with respect to y, let's compare that with this y coordinate for the vector field, 2xyz cubed. If I take the antiderivative of that, I jumped the gun a little bit, I'm sorry. If I take the antiderivative of that with respect to y, 2xyz cubed, then I get xy squared z cubed plus potentially some constant that might have x's and z's in it, because the partial derivative and partial integrals with respect to y will treat both x and z as just numbers. And finally, if I have a look at the z component, 3xy squared z squared, we have f of x, y, z is equal to partial integral with respect to z, and we get xy squared z cubed plus potentially some function containing x's and y's. Now let's compare the 3 representations of f of x, y, z that we have gotten. All of them contain x, y squared, z squared, and then some other term that we might need to match to somebody in one of the other representations. But looking among these representations, I don't see any terms that contain just x and z. None of these contain just x and z. I don't see any terms that contain just y and z. And I don't see any terms that contain just x and y. The only terms in play here contain x and y and z. And the other ones appear to be null, appear to be empty. No terms containing just x and y, no terms containing just x and z, and no terms containing just y and z. So our potential function, when all is said and done, we get to take f of x, y, z equals x, y squared, z cubed. And you can confirm that if you take the partial derivative with respect to x, y, and z for this function, then you'll get back the vector field that we had at the start. So this is a potential function. All right, that concludes this exercise. I didn't even need the second page that I set aside. So what we'll do as we continue on is, in addition to defining the curl of a vector field, we will define the divergence of a vector field, and then we'll use those quantities to establish some nice theorems for surface integrals.